Hello and welcome to this course on the physics of solar cells, what goes on inside to actually make them work, and how come the IV curve is shaped the way it is. I'm going to go through all the physics of that, but don't worry, don't freak out. It's not going to be with heavy equations and it's going to be fun, I promise you. My name is Mark Morose. I've been involved in solar my entire working life, and I think we're going to have a good time in this course. I started my career making solar cells and I haven't ever stopped. So upon graduation from college with a degree in physics, I started at Spectrolab, actually in 1974, making space solar cells. So this was right around the oil embargoes and so on. This was way before terrestrial solar was even the gleam in anyone's eye. But after Spectrolab, I joined and started with Arco Solar, the Kleenex of solar back in the 80s. And that became Siemens Solar. I joined Astropower. That became GE Solar. And then I joined SunPower and created the entire residential training program there from 2005 to 2010. Then joined EcoFirst and learned a great deal about solar thermal and PV together. And that was bought by SunEdison. So I rode that rocket. And then I joined Interplay Learning, where I have been helping to create an online virtual curriculum in 3D and VR space where you can actually assemble a solar system together in virtual reality. And now I'm working with Solar Energy International. So I've matured a bit in my life, learned a bit more about things, but have always still been in love with solar cells and IV curves, and hopefully that will come across to all of you. Going to cover these kinds of topics, so keep this in mind in terms of the arc of what we're going to go through. Going to go through some actual physics stuff here, but without equations to scare you away, but it's actually going to be real physics. So I know a lot of us deal with this stuff. Solar is wonderful. We know a great deal about it and we know how to use it and sell it and that it works. But often we don't have the time or the inclination to know, like, what's the guts inside? And maybe this will be the one and only time that you get to explore this stuff, then you can put it on the shelf. But I wanted people to be able to be exposed to the whys of how come this stuff magically works. What is the magic behind it? So we're going to start out by talking about why we dope a solar cell, and then review the current voltage curve, which, by the way, I'm not going to dwell on in terms of the 5 points, but I am going to spend the time of this course heavily focused on IV curves. Then we're going to mention the equivalent circuit of a solar cell in case you're not familiar with that, because that's going to help to explain a lot. And then I'm going to jump into some actual quantum physics of band gaps, which is what you see here. And it's going to help to explain some things that perhaps you've heard, perhaps you haven't heard, about how come this whole thing works. And then the whole focus of what I wanted to do in this talk was to explain how the IV curve gets its shape. How come it's shaped the way it is? We maybe know it and love it and use it, but how come it has that shape? It's pretty interesting. And then cover some environmental effects that we're all familiar with. For example, solar cells and modules lose voltage when they get hot. But why? What's the physics inside of how come it does that? That's what we're going to cover. And we're going to finish by dealing with the effects of shading on that IV curve and what I call the dolphin nose effect to the effect of shading. So that's what we're about to embark on. So let's get started. So why do we dope a solar cell, and what does that even mean? So silicon rocks on the left-hand side. The silicon is the second most abundant element on the Earth's surface, next to oxygen. And silicon and oxygen together make quartz, which is sand. So there's lots and lots of silicon. The key thing that we're going to focus on here, and I'm going to go from simple to complex pretty quickly. The key thing here is that silicon has 4 outermost electrons. It's got a nucleus with the protons and the inner electrons and so on. And then it's got these 4 outermost electrons. They're called valence electrons. These are the ones that are used in bonding, making crystal structures. These are the ones that are exposed and can link to other atoms and so on. The key thing here is that it's got 4. So what's that going to mean? Well, it means that every silicon atom, when you grow a crystal, is going to link up with 4 other silicon atoms. The figure on the left is the actual face-centered cubic structure that we get. In fact, the structure of silicon crystal is the same as that of a diamond. It's just that that uses carbon and this uses silicon. But carbon also has 4 outer electrons. So this would be the 3-dimensional structure of that silicon crystal lattice. What I'm going to do is draw it flat, like this, with all of those 4 bonds. And you see that every silicon circle atom is bonded to 4 other silicon atoms in a crystal, okay? So now, let's proceed to understand what happens when you take a hunk of silicon and put it in the sun. Just take a rock of silicon and expose it to sunlight. What's going to happen? we're going to have what's called Hole-Electron pair creation. And this is how it happens. You have a particle of light, which we call a photon. So we can think of light both as being a wave, that can bend, and you can bend it through prisms, but it also can be treated as particles, and we call those photons. A photon of light comes in, and on a random basis, it hits an electron in the silicon bond and gives up all of its energy. It goes away, and all of its energy goes into energizing that electron. And it gives it enough energy to break free. It basically ionizes the electron away from that atom, and now it's got enough energy to break free. It's no longer bound. It's now a conduction electron, and it can move through the crystal. But what happened? Everything was electrically neutral before that happened. But as soon as that electron is gone, you've now left a silicon site without a balancing electron, negative charge. So you've got a net positive charge in that area. And physicists have come up with a pretty complicated name for that. It's called a hole. It's like a bubble in water. It's a hole in the crystal structure where a charge could be, and it carries a positive charge. And this is what happens now. Just at room temperature, nearby electrons that are vibrating, running around, they're normally bound in those bonds, but it can vibrate enough, and it can vibrate over and fill that hole. And so now that covalent bond is now full, again, with one electron being shared by each silicon atom, so it's filled with 2 electrons, but it got filled back up again. But what happened? It left behind a space where it came from. And that now also carries a net positive charge because the silicon site has the same number of protons, but it's missing 1 electron, so its net charge is now positive. And then what can keep happening? A nearby electron nearby can vibrate, fill that hole, but then the hole is moved to another site. So what's happening is that we've created 2 free carriers of charge, electrons that carry negative charge and holes that carry positive charge. And these are now able to move around within the silicon crystal structure. Now, what can happen though is that lots of those electrons can wander into those holes and recombine and fall back in. And basically, you can have light come in, knock electrons loose, they recombine, and nothing comes out. All that happens is that the silicon rock gets hot in the sun. We don't want that. So the trick of everything I'm going to tell you now is going to be about how we design solar cells so that when those electrons get knocked loose and free, we get them out of there before they can recombine with the hole. That's the whole trick behind every solar cell that's ever made, no matter what it's made from. That's the main idea. I'm going to talk about silicon because it's used to make about, 95% of the world's solar right now. So it's pretty indicative, but the principle is true for everything. So now let's keep going. So how are we going to do this? How are we going to create a structure that sweeps out those electrons? Well, this is how we start. One way we're going to do it is to introduce the element boron into the crystal structure. What happens is that when we grow crystals, we melt rocks of silicon and they put in a little bit of very pure boron at that point. Then you close up the crystal grower, melt it, grow a big crystal, and the boron is sprinkled throughout. The key thing about boron is that it has 3 outermost electrons. That's what's the important thing about using boron. So when it fits in the structure, it will easily share with 3 other electrons, no problem. But there will be this 4th bond, this 4th covalent bond, that now only has 1 electron from the silicon, but it doesn't have an electron from the boron. There's nothing wrong. It's all electrically neutral. Everything's fine. But there is a space in which an electron could fit, okay? So now what's going to happen? Okay, you've got electrons vibrating nearby. They're going to be able to vibrate over and jump into that hole, and they'll fill it up. Now, excuse me, it wasn't a hole before. It was a spot in which an electron could fit into a neutral site. But now it brings with it a negative charge, and that charge stays there forever, day and night. This has nothing to do with light. So that electron moved over, and now what happened? It left behind a space where it used to be, which used to be neutral, but now it's got a net local positive charge. And then what can happen? Just like we saw, that hole can vibrate from site to site and can move around in the crystal. So what we've done by introducing boron is we've introduced particles able to carry a positive charge that can move around within that crystal structure. And so that's why this type of silicon is called p-type, positive type. The carrier, the free carrier that's able to move around here, carries a positive charge. even though it's basically an absence of a negative charge. It's like a bubble in water. So this is boron doping p-type. Don't be confused to think that we've somehow made a different kind of silicon. It's like p-type silicon is different. No, it's describing the crystal structure of regular silicon that has this dopant in it, okay? And don't forget that the boron site now has a permanent negative charge. This charge now is held in place. It can't move around like that hole. It's held in place. That's going to be important. Let's keep going. What do you think the other element is that we introduce? It's phosphorus. What do you think its characteristics are? The way that phosphorus is introduced is that now we take the big crystal that we grow, we slice it into very thin wafers, we put them into a diffusion tube, which looks like a big torpedo tube. It's about 1 foot in diameter and glows red hot. And into that is introduced a gas that contains phosphorus. And the heat is so high that the phosphorus atoms basically penetrate into the crystal structure and take a place. And when they do, phosphorus has 5 outermost electrons. So it has 4 electrons to share with the 4 silicon atoms, no problem. But the 5th electron basically is just dangling there. And even at room temperature, it has enough energy to just break free. And that electron now can just break through and wander in the crystal. So now we have silicon crystal structure that has particles able to carry a negative charge. And so that's why this type of doping is called N-type silicon, because of the negative type charge carrier. And now, just like before, the phosphorus site now has a permanent positive charge because an electron's been stripped away. It was neutral, but now it's stripped away. So it's missing the negative, so it's got a net positive charge that stays right in place and doesn't move day or night. That's going to be important. So let's do something with this. Let's put these guys together. So basically what we have here at the front, if you can see my arrow pointing around, the N-type region, typical for most cells, the N-type region is what's going to be the front of the cell. This is going to be facing the sun. The P-type region is going to be the bulk of the cell in the back of the cell. So let's do this. Let's introduce phosphorus to the front of the cell, which has its spare electrons that it's going to let loose. And let's build that in front of the bulk region, which is filled up with boron atoms that have these sites that could accept electrons. Now, just a note about this, typical solar cells, and different cells are made differently, but typical silicon wafer solar cells, this N-type region is pretty thin. A solar cell today is anywhere from, I don't know, 150, maybe 200 microns, 180, maybe 150 microns thick, pretty thin, but 150 microns. This front region is typically 1/2 of a micron out of the 150. So the front region of the cell that has this N-type magic is pretty darn thin. And we're going to see that light actually goes right through it, okay? But here's what happens, okay? In those diffusion tubes, when the phosphorus is being introduced in the dark, those electrons start breaking free and they wander and they find these holes and they go, great, this is a place where I could stay. And it goes and it stays forever. So what happens is that you strip electrons away from the phosphorus sites and you embed them and leave them in the boron sites. Now, when it left the phosphorus, it leaves a localized, fixed positive charge in the crystal. And where the electron went, it brings with it and holds a net negative charge in that area. And there's trillions and billions and zillions of these happening. So you build up a region of positive charge on the p-type, and then gradually as it moved over, you build up this sort of region, vertical, sort of a flat region of negative charge on the boron site. And this separation of charge creates a permanent electrostatic field that's created across the p-type, n-type junction, or the p-n junction. It's this electrostatic field that is the magic that we've been trying to create. We're going to see that this is what makes the solar cell work. And the magic of using semiconductors is that they are crystalline, so that when we do stuff to them, they hold the charges in place. It's not like doing it in copper or some sort of conductor, where the charges just move around however they want. These guys get held in place. And that's the magic, one of the many magics of semiconductors. So now, let's finish off this discussion by looking at what we've done. So remember, the front of the cell is pretty thin. It's, light can just go right through it. It's so thin. So let's now take this doped wafer of silicon and put it in the sun. Remember what happened before? It just got hot. But now a photon of light comes in, actually penetrates through the front, goes into the bulk of the cell. Think of the bulk of the cell as just being an absorber. It's just a bunch of silicon along for the ride with a bunch of electrons that can be hit by photons. So it gets hit. The electron and hole get created, hole-electron pair creation, remember? And that electron just starts wandering free. Remember, it just got knocked loose. And if it wanders into the field, we can deal with it. One of the sources of inefficiency of solar cells is that those electrons can wander the wrong way. And they can wander until they find a hole and recombine. So that's called electron hole annihilation or electron hole recombination. And the recombination current is something that manufacturers try to make small. They try to get the electrons out, but some of them recombine. So that's one of the sources of the fact that we're not 100% efficient. But if the electrons wander into this field, as soon as it does, it feels negative behind it, pushing, because light charges repel, and positive in front of it, pulling, and it gets accelerated out and pushed out to the N-type region and pushed to the front of the cell. And it happens pretty quick. And that's the key. Now we have a mechanism. The electrostatic field is like an electronic broom that sweeps electrons one way and gets them out of there before they can recombine with the holes. And then the hole, remember, also has a life, and it can wander. If it happens to wander this way and wanders into the field, it feels negative charges pulling it back and positive charges in front of it repelling it, because light charges repel. So it's repelled basically backwards, and it basically migrates to the back of the cell. And we're going to see this in future slides. So basically we have now a separation of charges with the electrons being pushed to the front and the holes being pushed to the back. And that's exactly what we wanted to make a solar cell work. So now let's put this together. Now I'm going to jump ahead and explain that a solar cell net voltage is about 1/2 volt. And we're going to learn about this by physics in a minute. But the voltage of a cell is about 1/2. That's not much, okay? So we end up wanting to put cells together in series to add voltage. 1/2, 1.5, 2, 2.5, 3. We make them into 40 and 60 and 72 cell modules. So let's look at what's going on there. Let's follow the physics here. Let's remember that we've got an electron in the silicon just sitting there, stuck, right? Ready to go. It's exposed to sunlight. The light comes in through the front, gives up its energy, creates a hole-electron pair. The hole, like we always know, is going to wander, and it wanders to the back. And I'm just going to show another one here, just because that happens in all the cells. This is all going on at the same time. But the electron wanders, and hopefully it wanders into the field. And when it does, it gets pushed out of the cell, and we've gotten that electron out. So now we've converted sunlight into electricity. Yay! And the net gain is about 1/2 volt. We're going to learn more about that later. But we end up coming out with electrons with about 1/2 volt. But now, this is important. What happens is that now that electron is connected by interconnect wires to the next cell. It flows into the back of the cell, finds a hole, and falls into that hole, and stops. The electron does not keep going. It's not like the light came in, knocked an electron loose, and it goes whoop, out and goes to the inverter and does its job. No, it just goes to the next cell, and it stops. It fills a hole, and it stops. And it says, okay, I'm here. What has to happen is that you have to have another photon of light, knock it loose, the hole-electron pair gets created, the hole wanders to the back, the electron gets pushed to the front, but now it came in with 1/2, it gained another 1/2, so now it has 1 volt, and it keeps going through. And as it goes through cells, it gains 1/2 volt at each step. But the critical thing here that has to do with shading is that all electrons have to be regenerated in each cell equally. So you have to have, effectively, the same number of photons hitting all the cells so that simultaneously electrons can leave one cell, go to the next, leave that cell, go to the next in a flow. That's why shading is so important, because if you cut down the number of photons in one cell, you've got all these other electrons coming in, and you don't have enough photo-generated current going out, and you get the dolphin nose. And we're going to get to that at the end of the lecture. But there's the idea, is that electrons go from cell to cell, and they stop, and they have to be regenerated with this hole-electron pair phenomenon. Let's finish up by putting it together. So now this is physically what cells look like connected, right? With the interconnect ribbons going from the front of one cell to the back of the next. Well, typically you use ribbons. They could be flat ribbons, they could be round ribbons, they might even be shingled. The basic idea here is that you're connecting the front of one cell to the back of the next. Why is that? Because you now have this flow where light comes in, knocks electrons loose, they go to the front of the cell, get into the ribbon or the interconnect somehow, flow, go to the back of the cell and stop, and are regenerated in that cell by new light, which then go to the front of the cell, go in the ribbon, go to the back of the cell and stop, and so on. So that's the actual physical look at how the electrons flow from one cell to the next in series, right? So we're getting to the idea of what we all know, which is how these guys are connected together and what's flowing. Let's put it all together into a complete module. Let's say you have a 72 cell module. So you have 72 cells in series, 72 of these processes going on, and roughly after going through about 72 and gaining roughly about a half, you end up with, let's say, 40 volts as your typical operating voltage out of that many cells. And then if you want more volts than that, you connect those together. So if we have a long string of modules, you basically have hundreds of solar cells all connected in series, adding 1/2 volt at a time, right?